Hi, and welcome back to Codex. Our speaker today is Mark Iwen, who is an associate professor at Michigan State University. Professor Iwen is an expert in computational harmonic analysis, mathematical data science, and signal processing. Today, he'll tell us about sparse spectral methods for solving differential equations. Take it away, Mark.
All right, thanks. Thanks a lot, Emily, and everyone over at Codex for the invitation. So I'm going to start off. This is sort of a two-part talk, so you can go to sleep during one part or the other, as you desire. I'm going to start off talking about what sparse Fourier transforms are, putting them into the general framework of compressive sensing, just to make sure everybody sort of understands the what you can get from these things. I'll show you a terrible looking theorem and go through it and show you it's not as terrible as it looks. Very exciting stuff in part one. And then in part two, I'll switch to the PDE part and talk about how you can use these sparse spectral methods or these sparse Fourier transforms to solve PDE. So let's get the show on the road here. So this is going to be joint work with my recently former graduate student, Craig Gross, whose irrational love for PDE was of great help in this, especially the second part of this work. So compressive sensing, for those of you who don't know or wish you didn't. What is the general framework here? So we want to recover effectively an element of a Hilbert space from a severely underdetermined set of linear measurements, the general compressive sensing framework. We have incredibly underdetermined sets of linear measurements, so we try to make up with the fact we have fewer than you would generally need by having some model that we assume X is near, which is going to help us resolve the indeterminacies of our underdetermined set of linear measurements. Okay, so given this, there are a bunch of questions that you immediately have to answer. You have to figure out which types of linear measurements make sense for your choice of Hilbert space and sort of model class. And of critical importance for part one of this talk, what sort of computationally tractable inversion methods do you have for your choice of H and M in order to be able to recover X when you have your linear measurements? All right, so the most standard setup that everyone who knows what compressive sensing has seen is where your Hilbert space is k-dimensional Euclidean space, and your model space are all vectors which have at most S non-zero entries. So you have sparse vectors that you're aiming for. Take fewer measurements, you can recover them. There's been work where you change your model class in Euclidean space to be some other type of geometrically simple set, like a low-dimensional submanifold with bounded reach, something like that. You can consider matrix completion problems and have your Hilbert space be K by K matrices and your model class be low-rank matrices. Okay, today, the setup is we're going to be considering L2 functions from some d-dimensional domain, functions from 0, 1 to d into complex numbers. So this is our Hilbert space. And our model class are going to be periodic functions whose Fourier series coefficients are at most S sparse. So still a sparsity sort of model assumption here, but it's on the Fourier coefficients of our functions into the complex numbers. Biggest difference here from the standard setting is that this is an infinite dimensional Hilbert space. So there's going to be some index set I floating around in some slides later. It's there because we have an infinite dimensional Hilbert space. And so when you see it, I'll comment on that again, and it'll make a little bit more sense now why it's there, hopefully. Okay, so.
Hey, Mark.
Yes.
Just so I'm clear, that M is just trig polynomials, right?
Yeah, exactly. Yep. So exactly. Here's the one-dimensional setting where I was going to make that point, hopefully even more clear, but excellent question. It's like I set myself up. Yeah, so if we look at functions of one variable, that's exactly correct. The model space are sparse trigonometric polynomials. So here's a one-dimensional setting. I have a function from 0, 1 into the complex numbers. It's I'm going to sort of control where the frequencies are going to be, the maximum degree of a trigonometric polynomial that I'm going to consider. Basically, I'm going to use a bandwidth parameter k, I'll call it, to sort of have the maximum degree that I'm going to consider. And then I need to find s integers inside of this range that I'm going to use for a best trigonometric polynomial approximation of g. And that's the trigonometric polynomial approximation version of this problem, exactly. So what are my linear measurements? I'm going to take point samples. So they're going to be determined by some grid points, effectively, if you want to think about this from a numerical methodsy type of way. Then I'm going to pick in 0, 1, where I'm going to take point samples. And to make point samples actually meaningful, I'm going to assume that G is smooth enough that taking a point sample actually is not just sampling a discontinuity or something. So we're going to have my Fourier coefficients be in little L1. We want to try to aim for near optimal error guarantees, best S-term approximation error guarantees, a la Devore, Cohen, many others have thought about. So to do that, we're going to need a number of function evaluations and grid points, which scales like S times log factors of K. So that's going to be kind of what we're aiming for here. The biggest difference between, again, sort of standard compressive sensing techniques and these sparse Fourier transform things is that we're going to restrict our recovery algorithms to also be linear, have a linear runtime in M. Okay, so maybe quadratic in M at worst. So we want so-called sublinear-time algorithmic recovery results here. Sublinear meaning that if S is much smaller than K, then the runtime of my compressive sensing method here has to be faster than the time it takes to simply enumerate the possible frequencies which could exist in a best trigonometric approximation, right? So I have to do this very quickly in order to sort of qualify as a sparse Fourier transform in this setting. So in the discrete case, there are results like this going back about 15 years or so due to Anna Gilbert, Piotr Indyk, and a bunch of other folks. In this first part, I'll show you deterministic results that hold for all d greater than or equal to 1. They'll come in handy when we're talking about approximating functions of many variables using trigonometric polynomials, and sort of give you fixed grids that you can always use on the d-dimensional torus for solving that problem. Okay, a little bit of fun motivation. So why did people start thinking about these things in the first place? Sparse Fourier transforms, why is runtime potentially important in applications? So there are a whole bunch of engineering applications where humans have engineered frequency sparse signals. And sometimes you don't know exactly where the frequency content is going to be in advance in certain situations. So my favorite example of that was these frequency hopping modulation schemes, which were introduced by Hedy Lamarr, this sort of famous World War II era actress, Hollywood actress, but much more interestingly, also inventor and interested in mathematics and engineering. So the way these things work are effectively you have two parties who want to communicate, fix a random number generator, synchronize it. And then when you're talking on your radios, the frequencies that you're communicating, sending and receiving on are jumping all over a really huge bandwidth as you talk. And if somebody's trying to listen in on you or jam you, they find you at some moment, they'll be frustrated because you'll hop to another frequency quite quickly and start talking there instead, right? So if you want to try to defeat these types of frequency hopping communication schemes, sparse Fourier transform or something similar to it would be helpful, because if somebody hops to a different frequency, you might be able to very rapidly figure out what that new frequency is in a sort of time that's sublinear and a huge bandwidth they're hopping around in, and start listening in or jamming them again. So this is kind of the motivation for these things. There have been applications in faster GPS and other applications as well. The main thing that I'm interested here, though, are these multiscale PDE and high dimensional PDE applications that were first considered by Ingrid Dobeschi about 10 years ago, where we'll be applying these things now. Okay, so here's a theorem that we're going to need later. One of these results. You sort of set it up like this. Again, we're going to need, here's the script I set that we're going to need to truncate the frequencies of this thing. You get to choose this finite set of frequencies any way you like. But it can be relatively large, something like k to the d, but you have to have some idea where the spectral information is going to be in your function to begin with. And then after your choice of I, what you're going to do is sample your function defined on the d-dimensional torus. It can be, the samples you acquire can be corrupted by errors of magnitude less than or equal to e infinity. So there can be noisy function evaluations. And then one of these methods will produce a sparse approximation, G sub s to the Fourier series coefficients of G, that satisfy these sort of not very pleasant looking error bounds. So what do these error bounds, sort of take a closer look at them? They're going to be best S term approximation error bounds for your Fourier series coefficients restricted to the set I you chose. Okay, so that's what this first term is. There's going to be another term that penalizes you based on whether or not you made a good choice of I. If you choose I very stupidly, then this term will be large. If you have at least some basic idea where your the energy of your function is in Fourier, it'll be small. And then you have your sort of potentially arbitrary corruptions on your function evaluations, right? We have 1 and 2 norm errors. Most crucially here, the number of function evaluations as well as the runtime of the recovery procedure that gives you these trigonometric polynomial approximations is going to be only linear in D, the dimension of your domain, times quadratic dependence on your sparsity, times additional log factors. So this is for an entirely deterministic method that gives you a deterministic grid of points on the d-dimensional torus that will always allow you to satisfy these error guarantees. If you don't like this quadratic dependence on S, though, then there are other randomized algorithms you can use that subsample structured subgrids of this deterministic grid, and then with high probability allow you to satisfy these error guarantees for a fixed function G with a number of function evaluations now that's linear in S. So to a variety of different techniques that you can use here, and we're going to need these things later. So maybe just a couple fun examples of, I don't know, very simple techniques you can use to prove these sorts of results. So I'll give you just some idea of how you might set this up and start at least proving simple versions of this type of method. So let's look at the following compressive sensing problem that we're going to turn into a very simple sparse Fourier transform. So here we have a one sparse vector. I'm going to call it G hat. So like the discrete Fourier transform coefficients of a vector G. And here's my compressive sensing matrix B. I'm going to form it using 2 prime numbers, 2 and 3. And what I'm going to do with each of these primes is I'm going to take all residues, mod these primes, and then for the associated row of a residue mod a prime, I'm going to take the column number and just put a 1 in that entry if it's congruent, if the column number is congruent to that residue mod that prime. So here, counting from 0, 0 is congruent to 0 mod 3, 3 is congruent to 0 mod 3, etc. Alternatively, these are just 2 by 2 identity matrices and 2 3 by 3 identity matrices you can use to fill this out. Okay, so we construct the matrix this particular way. If you go ahead and multiply this matrix by this vector, your resulting measurements that you get to observe are going to be the one non-zero entry repeated twice. And the position that it's repeated will tell you what the original entry was congruent to mod both 2 and 3, which tells you, which will allow you to determine where the original entry was using the Chinese remainder theorem. And you get 2 estimates of what the value was at that entry. You can average them and see that the entry is 3.5 or something. Okay, so you save one linear measurement here over the sort of brain dead approach of making this the identity and effectively looking at each entry individually. Okay, so let's take this now and turn it into sort of a simple sparse Fourier transform by multiplying by a discrete Fourier transform matrix and its inverse, and then regrouping. So if I take the discrete Fourier transform, the inverse discrete Fourier transform of this frequency vector, I have samples now that I'm allowed to look at of my original vector G. And over here I have a modified compressive sensing matrix, which is my previous one times the discrete Fourier transform matrix. And I can further simplify this a decent amount by noting that each one of these rows is like a spike train, a discrete spike train that I'm multiplying by a DFT matrix. So there's going to be a lot of structure when I multiply them together. In particular, the 2 rows associated with 2 are both going to have only 2 non-zero entries in them. The 3 rows associated with 3 are only going to have 3 non-zero entries in them. And I'm going to get 2 columns that are entirely 0. Okay. Those 2 columns that are entirely 0 means there's no point in my looking at the second and last entry of G at all. I just multiply it by 0 anyways. So I really only need to look at 4 of the entries of G in order to compute the exact same right-hand side that I had before. Okay. And I can further factorize that matrix and see that really all I'm doing here are computing 2 smaller Fourier transforms of subsampled entries of G, right? So I can do this in parallel with 2 FFTs quite quickly and still get the same measurements that I had before. And so I can reconstruct where the non-zero frequency was the same way that I did before. Right? So this is a very simplistic sparse Fourier transform when you have 1 frequency sparse functions. You then generalize to S sparse in Fourier functions and then to compressible in Fourier to get a nice one-dimensional result for approximating functions of 1 variable. And you can then wonder how to start thinking about extending it to a function of D variables. And that's where, again, sort of a nice idea called rank 1 lattice techniques come into play that'll let you sort of figure out how to get a start generalizing to functions of D variables. So the way that this works in a picture is you have your function G defined on a D-dimensional torus, right? So we're going to wrap a path around the D-dimensional torus. This path is going to be determined, its sort of initial direction is going to be determined by a vector Z that we choose however we like. So that's what the Z is here. It's a vector with integer entries. And if I restrict my function G to its values on this path, I have a function G tilde, which is now a function of 1 variable, right? And if I take the discrete Fourier transform of G at frequency K and sort of write out what it's going to be in terms of this G tilde that I've defined using G, I can see that if I compute the Fourier series coefficients of G tilde, this function of 1 variable, using whatever nice method I have for computing Fourier coefficients of a function of 1 variable, I'm going to get exactly Fourier series coefficients of this function of D variables, except at a frequency that's equal to that frequency vector K dotted with Z, which I chose, right? And so if I choose Z well, and I'm able to figure out how to map these frequencies that I'm able to learn from my one-dimensional method back to these frequencies K in an efficient way, I can take a sparse Fourier transform on functions of 1 variable and use it to get a function, a sparse Fourier transform for functions of d variables. That's another sort of proof element that's sort of baked into these things. Okay. Great. So again, you put all these techniques together and a whole bunch of other modifications and things, and you get this theorem that we saw before, which we're going to refer back to in part 2 of the talk, which we are about to move into. So that is part 1. So if you've fallen asleep or otherwise decided you didn't want to pay attention to the end of part 1, you can re-wake up now and learn something about Fourier spectral methods if you feel so inclined. It's somewhat independent, starting off from here again in part 2. Okay, so let's talk about how you can solve, as an example, a stationary diffusion equation. So what we have here is our PDE data in the form of a diffusion coefficient A. Again, it's a function of d variables defined on a d-dimensional torus. So we're assuming periodic boundary conditions here. And a forcing function f, again, defined on the d-dimensional torus. So these two functions are given, or at least we are we're allowed to sample these. And then given knowledge of A and F, our job is to go ahead and learn U given A and F. So our solution U is what we're after. Okay, so we want to approximate U as best we can. So how would you do this using a traditional Fourier spectral method? Okay, so you can do it in the following way if you want. I'll make you, in approximately 3 minutes, I'll make you an expert on Fourier spectral techniques now. So all we're going to do is expand our forcing function and our diffusion coefficient and our solution in terms of its Fourier series coefficients. Right, so I'll do that here. Here's my solution expanded in terms of its unknown Fourier series coefficients. Again, at least in theory, we know the Fourier series coefficients for both f and a. I can now take my gradients in and simplify, and I get this beautiful looking equation in terms of the Fourier series coefficients of a, u, and f. And if I match up coefficient by coefficient, I see that now solving my PDE is really equivalent to just solving this infinite linear system. So I know the right-hand side, which are my f's, the Fourier coefficients of my f's, at least in principle, I know them. I know the matrix effectively on this side. It's determined by the Fourier coefficients of A. Looks like some sort of convolutional system. And I want to solve this linear system for my unknown coefficients U. Right? So just a linear system. There's nothing that complicated going on here. So let's think about solving this linear system. Okay. So it's easy, just a linear system, except, well, it's an infinite linear system. So we're going to have to, on any computer that I'm aware of at least, truncate this and solve a finite version of this infinite linear system. Okay. Even truncation is going to be potentially bad, though, because if D is quite large, I'm probably going to need quite a huge linear system to solve in order to get a decent approximation. And I need to choose that subset well. This is like coming up with a good choice of that truncation set I that was floating around in the theorem before. I need to truncate it well. And even in this situation, finding the Fourier coefficients of f and a can be challenging if I only have sampling access to f and a, and it's a D is 1,000 or something really huge. I mean, it can be quite difficult to find these Fourier coefficients. All right, so what you would generally do is hope that some type of FFT variant would save the day. And so what do FFT variants do that are nice? So first, they enforce a basis truncation on the way they're developed. So you're going to concentrate on the lowest frequencies. And that makes sense in this PDE context because you know your solutions are going to be smooth. So hopefully they'll be pretty well represented by trigonometric polynomials supported on the lowest frequencies. So that's good. And your FFTs then, based on this truncation, are going to allow you to approximate the Fourier coefficients, the true Fourier coefficients of f and a. So you'll get hopefully accurate approximations of the parameters that make up your linear system that you need to solve. And you'll get them relatively fast, except maybe not that fast if D is quite large. So if D is 1,000, an FFT is still going to be too slow. So instead, you do something entirely brain dead. You change the F in FFT to an S and use a sparse Fourier transform instead, and think about how you can possibly make this work in that setting. So that's all we're doing here. So here's the slide that'll tell you not only how we're doing it, what the solution approach is, but also how you can prove that it works in certain situations and get theoretical guarantees about approximating the solution of this diffusion, such diffusion equations, for example, quite accurately. So we're gonna sort of be motivated by Say's lemma here, really nice result. And it says the following. So here is our original, remember, infinite linear system that we're trying to solve for U, the Fourier series coefficients of our solution. And what Say's lemma says is, well, suppose you truncate this infinite linear system somehow to a finite version. So I'm only going to solve a portion of these linear, of the linear equations that I have. And not only that, I'm going to solve like a noisy version of that portion of the equations. So I'm going to have approximations to my true Fourier coefficients of f, and I'm going to have only approximations to my true Fourier coefficients of a, right? I'm going to solve this noisy finite version of the true infinite linear system, and then I want to know, well, how does the solution I get from the trigonometric polynomial determined by the solution differ from the true solution U? And it differs in the following three-term bound that you get from the lemma. It says, well, it's going to be bounded by the error you would have just approximating U by a trigonometric polynomial projection onto its Fourier series coefficients in I. So if you choose your set I wisely and you have a good approximation to U by a trigonometric polynomial in here, you're going to be in good shape. And it's also going to, of course, depend on how noisy your approximations of the true Fourier coefficients of f and a are. Okay, so what are we going to do instead? Well, we don't want to use an FFT. It's potentially too slow when the dimension of the problem is too large, for example. So I'm going to use a sparse Fourier transform to approximate these Fourier coefficients of my diffusion coefficient function A. I'm going to use a sparse Fourier transform to approximate the diffusion or the Fourier coefficients of my forcing function F. Then I'm going to take the support information that I've gathered about the forcing function and the diffusion coefficient and use it to determine a good truncation set, a sort of adaptive truncation set for my solution U. And then once I've decided on my truncation set I, and I have my approximate Fourier coefficients, I have a well-defined linear system that I can just solve and get a solution V, which is going to be accurate, guaranteed to be accurate as long as my set I was chosen in a decent way and I get sufficiently accurate approximations of my Fourier coefficients. So this is exactly how the method works as well as why the theory works. SFTs, if you have compressible diffusion coefficients and forcing functions, will reduce these two error terms to be relatively small. And we'll discuss later how well you can guarantee that you choose a good truncation set, which will then make this term small, and so you'll get a good bound on your solution error. Okay, so first, though, it would be nice if they actually worked numerically, and they do, or else I probably wouldn't be giving this talk. So here's a toy problem, just one-dimensional problem. I have 2 sparse diffusion coefficient, 3 sparse F. Here's a sparse Fourier transform based spectral method as outlined on the prior slide. So I compute from samples of A and F trigonometric polynomial approximations and solve the linear system, and for the Fourier coefficients of my solution, plot the results. As S increases from 1 to 2 to 3, I get numerical convergence, right? For a standard FFT-based spectral method here, it's entirely determined by the degree of the trigonometric polynomials that you're going to allow yourself to use to approximate A, F, and U. There are relatively large frequencies in here that you have to resolve, so you're not going to get good convergence until K is larger than 150, and you have to go until it's about 400 or something before you get convergence of to the same level as errors you get over here, right? Sort of clearly, if you don't know what K is and you have to increase over many, many guesses of what K is, sort of doubling your prior value, this is going to take a lot longer than this. Two-dimensional version, same thing works. You can code it up. It's relatively simple. You can solve, again, I just have a two-dimensional problem here, same sparsity levels. Here's the errors as you increase sparsity and as you increase K, which is your, again, trigonometric polynomial sort of bandwidth size. And the main thing here about runtimes is that an FFT is K to the D times log factors runtime, where D is the dimension of the problem. And these sparse Fourier transforms are just sort of log linear in D. So as you increase D, you can solve problems using a sparse Fourier transform that you can't even sort of start solving with a regular type of FFT-based method. Okay, so how do you find a good adaptive truncation set for our solution? That's this first red term. How do we control this error? Using the support information that our sparse Fourier transform returns about F or and A. So that's the next question we'll talk about here. So if you look at the linear system that you're solving in the Fourier basis, it has this sort of convolutional structure. It's a banded matrix. And we're multiplying this matrix by our unknown solution U and trying to have it satisfy the right-hand side, which are the Fourier coefficients of our forcing function. So the only elements of the Fourier coefficients of U that we don't know that are going to be interacting with our solution are going to be spaced out according to the banded structure in this matrix, which is dictated by the support of A hat, right? So if you think about this for a second, the following sort of stamping set method for determining a good truncation set for your frequencies might be what you come up with next. So let's just show you an example of what these things are, how you build them. So what we're going to do is take the support in Fourier of our diffusion coefficient. So that's these little things mark the frequencies that are active, that have high or large magnitude Fourier coefficients in A. Here are frequencies that are active, have large Fourier series coefficients in the forcing function F. And what we're going to do is create a truncation set by using a so-called stamping set. And this is how we're going to build our stamping sets. So for n equals 0, our sort of 0th level stamping set, we're going to include the support of the forcing function. Our linear system, we're trying to match to the right-hand side of which are the Fourier series coefficients of f. We certainly need to solve the equations where it would make sense. We need to solve the equations where the magnitude of the right-hand sides of those equations are largest. So those are going to be given to us by this information. And then the other equations that we should include based on this idea that the Fourier series coefficients of our solution are spaced out according to the support can be recursively defined by doing a Minkowski sum of the support of A with our support of the forcing function. So here's our 0th level stamping set. Our 1st level stamping set is going to be to toss in the support of our diffusion coefficient centered on each one of these forcing function frequencies. And then we'll just keep adding them in, adding this stencil in around each one of these points as we increase n, which is our stamping set level. So we recursively build up our stamping set levels that way and use that as our truncation set. Okay, so our truncation set I is now one of these SN sets defined this way. And so our first term in Say's lemma now is determined by our choice of n, or determines how we want to choose n. Okay, so we put all of this together, and we get the following theorem. It says, use a sparse Fourier transform to approximate the Fourier series coefficient of A and F. Then go ahead and use the stamping set construction technique we just discussed to truncate your infinite system of linear equations. Solve this now entirely well-determined linear system for your approximate solution U hat KSN. Then the error between your solution you obtain, the trigonometric polynomial determined by these Fourier coefficients, and the true solution is going to be bounded by a term that decays exponentially in n, at least in certain situations. I'll show you where this constant A comes from and how you can bound it, plus errors that depend on how accurately your sparse Fourier transform works to approximate the Fourier series coefficients of f and a. Right? And again, those sorts of terms from the first part of the talk can be bounded by best S term approximation sort of guarantees of the following form. Okay, so if you choose your sparsity well enough and you actually have compressible diffusion coefficients and forcing functions, and if you choose your stamping set level large enough, you can control your approximation error and get good answers using this sort of technique. Okay, so what is this constant A? How can you bound it or make some sense of it in some situations? So it's determined by the diffusion coefficient in the following way, or this is one way of determining such a constant A, I should say. So here's our diffusion coefficient function A. A min is going to be the small, it always has to be positive. A min is going to be the closest it gets to being 0 ever. So that's what A min is. And then we're going to look at the deviation from its mean. Okay. And you can define this constant A in this sort of situation to be the deviation from the mean of this function over A min minus twice the deviation from the mean. Okay, so if it oscillates a decent amount but doesn't ever get well, it's oscillating too close to being 0, then this constant can certainly be less than 1, and you can have this exponential convergence we saw in the first term of Say's lemma. Okay, so let's kind of wrap up here and think about what the overall complexity of this method is and how it depends in particular on the dimension of the domain. So we're going to use 2 sparse Fourier transforms to set up the linear system we have to solve. And then we're going to have a relatively sparse, it turns out, linear system to solve that's going to be the cardinality of the nth stamping level set by the cardinality of the nth stamping level set. Okay. Each sparse Fourier transform, we've gone over this before, is kind of log linear in the dimension D and linear in the sparsity S if you are doing it with high probability kind of recovery of a good answer. And you can bound the cardinality of these stamping sets in the following way. So it's going to be the maximum of S to n plus 1 to the minimum of S to n plus 1. This is at least an upper bound. In general, it's going to be a bit smaller than this, actually. But this works. If you fix your stamping level to be some n equal to 5 or some sort of constant, right, then this is going to scale like S to the n. So it's going to look, for large sparsities, it's going to look polynomial in S. All right. The dependence, most importantly, on the ambient dimension of this entire thing is going to be linear or log linear, right? There's nothing in here that has to do with what D is. It only depends on your choice of sparsity and stamping set level. The only place D shows up is in your sparse Fourier transform runtime. So we have very mild dependence on the dimension. And even if you want to let n go to larger values, larger than S, you have exponential dependence on n being computationally mitigated, by which I mean it's going to look like, if n is larger than S, it's going to look like n to the S. So it'll be polynomial and n with the power being whatever your sparsity choice is. So again, potentially, depending on your choice of S, a large polynomial, but sub-exponential. So you're kind of avoiding the curse of dimensionality here if you are lucky enough to have forcing functions and diffusion coefficients that have compressibility in their Fourier coefficients. All right, so just to prove that you can actually solve 1,000-dimensional problems, we solved some. The final set of experiments here. Here we have error in our solution, or at least a proxy for the error. It's a provably good proxy. So we compute our solution, USN, push it through the PDE to get an approximate forcing function after we apply our linear operator determined by A to it. This error is going to be a bound on the error of between U and our approximation to U. Okay. There's no method for solving exactly what U should be when you have 1,000-dimensional problem, so proxy is the best we can do. Our diffusion coefficients in F are randomly chosen with 51 and 2 frequencies respectively for these sort of examples, where our frequencies are have a bandwidth parameter set to be 1,000. So for these 1,024-dimensional problems, there are 1,000 to the 1,024 possible frequency choices that we are choosing from in order to set up our PDE and solve. And it should also hopefully be clear at this point that it would be simply impossible to use an FFT or any method that's even linear in the potential size of this basis to even start solving this thing. So you have to sort of go sublinear or die on a problem of this dimensionality. And one other final thing, so we are focusing a lot on getting provable error guarantees for diffusion problems. Sure, maybe you don't care about diffusion problems. You can solve more complicated PDE as well, as long as you have this approximate sparsity in the PDE data. So here's an example of an advection-diffusion-reaction equation in 3 dimensions. We have now PDE data, diffusion coefficient, and additional functions B, C, and F, right? They're all sparse in the Fourier domain. And we're plotting error proxies for different choices of stamping set level and sparsities, right? You can get down to errors on the order of a few percent, relative errors on the order of a few percent. And solve these sorts of equations, see the multiscale structure of the solutions and slices through the three-dimensional solution space. So you see the sort of higher order and lower order ripples of this thing, and you're being able to find them. So you can solve it for more interesting types of PDE as well that have applications to things like, for example, contamination transport through underground bedrock, things like that. So would be an example of a modeling application involving an advection-diffusion-reaction equation, for example. Okay, so anyways, that's it. Thanks for listening. If you're interested in seeing anything in more detail related to the talk, here are some references for you to check out should you decide to.
All right, let's thank Mark by smashing those reaction buttons.